Hello everyone, this is Dr. Lennon, and we're going to be talking about functions of several variables. We're really going to stick to two input variables, so basically we're going to go from functions whose graphs are 2 dimensions to functions whose graphs are 3 dimensions. If we talk about single variable functions that we've studied so far, what do those look like? They look something like y equals f of x. And typically that's some kind of formula with a bunch of other numbers and x. So I would say it's a formula in x. Okay, so this basically has one input variable or independent variable, x, and it has one output variable. And that output variable we talk about as y. So now when we talk about functions of several variables, we want to increase the number of inputs. So we're now going to have still one output, but several inputs. So let's talk about a two-variable function. This is basically what we'll be moving up to. You can talk about functions with several more variables. You can have 3 or 4 or 10. As many as you want, really, but we're going to stick to two input variables, and then that way when we think about their graphs, those graphs can be visualized in 3 dimensions. A lot of times when you move up with several variables, it makes sense to talk about them, but if you want to think about them as functions, you can't really think about their graphs that well because they'll be in more than 3 dimensions, and that's difficult for us to visualize. So now these things will actually... usually for the output variable, we're going to use the letter z, and our two inputs will be x and y. So we would write z equals f of x and y, and this will now be a formula in both x and y. So you'll have numbers multiplied and added together and all the other math type of operations that we've seen put together with x and y. So here we still have our one input variable, or excuse me, now we have two input variables. Two inputs, x and y, and we have a single output variable z. So let's go ahead and look at how we can evaluate some of these things. So now when you would graph these things, we actually have ordered triples. Let's go ahead and look at evaluating a couple examples and then talking about their domains. And basically that's all we need to do to get our foot in the door where we can start talking about partial derivatives. Okay, so let's look at some examples where we evaluate some functions. So first example. Let's say we have, so we'll just say evaluate given, so our function now f of x comma y is going to look like x squared over 1 plus y squared for this example. So again, our output values when we plug in numbers are going to be z values, and our formula here, x squared over 1 plus y squared, notice it's has both inputs involved. So let's say we want to figure out f of negative 2 comma 0. Well, then we take the formula and we just replace x by negative 2 in parentheses, and we replace y by 0. So we end up with just positive 4 over 1, which is 4. So basically, what that means for us is the ordered triple x, y, z equals negative 2, 0, 4 is on the graph of our function. And a lot of times these three-dimensional functions can look kind of complicated, so we require some computer software to graph them. If you just want to graph a single point, I can show you how to do that. So what does that look like? Well, we need 3 axes, so it looks a little weird in 2 dimensions, but we can still do it. So let's suppose we wanted to graph this point. How would we do that? So kind of like a side question. Let's graph the point. -2, 0, 4. This isn't the whole graph, we're just graphing a single point. So basically how you draw your 3 axes is we'll draw x's got a negative input, so we'll draw x here. So this is our x-axis, and then we'll draw our y-axis this way. So this will be our y-axis, and then this right here we can draw as our z-axis. So you have to indicate which way is going to be positive and which way is going to be negative. So in 2-dimensional graphing, the 2 axes divide our space into 4 places, so we have quadrants. In 3 dimensions, these actually divide our space into 8 sections, which would be octants. So if x would typically be positive in this direction, so this would be +2. So in this direction, we would be at -2. Y, we're at 0, so that means we're basically going to be on the z-axis. So going up would be positive for z. So our point would basically be up here, and then we would go out parallel to the way our x-axis runs, and we would have this point. So this would be our point. So this would be -2, 0, 4. Basically, we're going in the x direction 2. We don't move in the y direction because the y direction is 0, and then we go up 4. So that's how we get the z graph there. So that's how you would graph the single point. Okay, let's go ahead and continue with this example. So let's plug something else into our f of x, y function. So let's say b, we want to do f of -1, 4. So let's remember our function was -x squared. So we're going to have -1 squared divided by 1 plus 4 squared. So this comes out to 1/17. So again, our ordered triple here. You don't have to write this, but I just want to indicate it since we are just getting introduced to multivariable functions. Would be x would be -1, y is 4, and our single output here is 17, 1/17. So that would be our ordered triple that we have. All right, let's do one more function, and then we'll move on to talking about the domains of these things. So example, let's evaluate again, but now our function will be g of xy equals x squared e to the 3y. So we have a, we want to evaluate g of -3, 0. So plug in -3 for x, we get -3 quantity squared times e to the 3 times 0. Well, that ends up as 9 times 1, which is just 9. So our ordered triple here, x, y, z, is -3, 0, 9. And for b, let's evaluate g of 1, -1. So here we want to plug 1 in and square it, and then we do e to the 3 times -1. So this just comes out to e to the -3, or 1/e cubed. If you want a decimal, you can plug that into your calculator. It's going to be some small number. Comes out to 0.05 if you round to 2 places. So here our ordered pair x, y, z is 1, -1, and 1 over e cubed. So I will show you a way where you can look at the graphs if you actually want to try and graph these functions and see what they look like. So the website I like to use for that is GeoGebra. So you can just Google GeoGebra 3D calculator, and you can just type in the functions. Desmos has some options, but they're not as easy for 3D graphing, which is what we primarily use for 2D. So let's look at our first one. So I think we can just do them as z equals, let's say, the first example where we had some points, z equals x squared over 1 plus y squared. So we get something like this, and we saw some points that we had on there. -2, 0, 4, I think was one of those points. So can we find that point? We could graph a couple other things and see the intersection. Sometimes that'll help us, but you can kind of move it around and see. So let's graph. It'll be the intersection point of a couple of these planes. Let's say we wanted to graph x equals -2. We see that plane there, and then we could also graph let's say y equals 0, and then lastly we could graph z equals 4. And we have the intersection point of those 3 planes is the same as our ordered pair right there. So notice you can kind of see our graph hits exactly that point. So we can see that our graph goes through this point where those 3 planes intersect. And that actually helps you see that we are dividing the plane. If you have 3 planes, an x value equals a number, a y value equals a number, and a z value equals a number, you do divide the plane into 8 spaces, 8 kind of compartments. But you can kind of play around with this yourself. But we see we're getting that point right here, that intersection point, -2, 0, and 4. So that's the point that we graphed. So that's a little bit maybe helpful in terms of the visualization. And you have to remember that these things continue in all directions. So, you know, it's not as if they just stop. We're just seeing a section where this function is graphed in 3 dimensions. Okay, so let's talk about the domain, finding some domain and giving some examples. So let's make a remark, let's say. So when we find the domain, of a function that has 2 inputs, so right, e.g. z equals f of x, y. The restrictions are placed on x and y. So for that reason, we can view the domain as a subsection of the xy plane. So a lot of times when I ask you find the domain, I'll also ask you to sketch the graph of the domain. So let's go ahead and run through a few of those examples. So example we will say find the domain of each function and sketch a graph of the domain. It's a little repetitive. I could probably word that better. But this way it's clear at least. So let's look at this first one. Let's say f of xy is the function, the square root of x plus y. So when we're finding the domain here, again, our functions we're talking about in this course are just real valued functions. So we need for our output to be a valid real number. So for that reason, finding the domain here, the domain has to satisfy x plus y has to be bigger than or equal to 0. Because if x plus y were a negative number, we would be taking the square root of a negative value. And so that would not be a real output value. So we can subtract x, and basically this inequality is going to give us the restrictions on our domain. So the only way our z values are going to be real is if we plug in some y that is greater than or equal to negative x. So what we can do is we can graph that. We know that y equals negative x is the 45-degree angle line through the origin with a slope of -1. So our graph looks like this. This is the y equals negative x line, and then we want the y values that are bigger than negative x. So that is shading this region up here. So our domain for the function f of xy are all the ordered pairs that you can plug in the shaded space. So that's exactly our domain. So this is the graph of the domain. Or in particular, the domain of f of x comma y. So we just need to make sure that all of our outputs are valid based on the ordered pairs we're plugging in for x and y. So let's go ahead and do another one. B. Let's look at g of xy equals x times the natural log of y. Now, x is fine. You can plug in any number for x, and that's not going to cause any problems. But here, we know that the input of the logarithm is only defined for positive inputs. So here, our domain is just given by y greater than 0. And if you want to graph y greater than 0, so we cannot include the y-axis. So that means we want to put a dotted line over the top of it. A dotted line means it does not include it. So we have a dotted line there, and then we want the positive y values. Oh, sorry, I dotted the wrong axis. So we want y greater than 0. Y equals 0 is the x-axis. So we want to dot horizontally. So y greater than 0, the line y equals 0 is the x-axis. So in fact, what we want to do is we want to be dotting this direction. And then we want to shade above it. And that is the domain of our graph. So that's the domain of g of xy. Okay, so those are pretty straightforward, just graphs of inequalities of lines. Let's look at a few more interesting examples. So let's say this example is h of xy equals xy divided by x minus y. Well, in this case, the only problem for the domain is we cannot allow division by 0. There's no square roots or no other functions that have domain restrictions. So here the domain is just going to be given by x minus y cannot equal 0, which means x cannot equal y if you add y to both sides. So the only problem here would happen if x is equal to y. So the domain is just x cannot equal y. So basically, if you would graph that, x equals y is the 45-degree line through the origin. So we're going to dot that. And basically, any ordered pair would work except for ones on the dotted line. So we would shade the entire space besides that dotted line, and that's going to be our domain here. So this is the domain of h of x, y. And then D, let's look at one last example. Let's call it f of x, y again. We get e raised to the x, y power, and then we're dividing by y minus x squared. So this one's a similar story. We don't want to allow division by 0, so basically y minus x squared. This thing cannot equal 0. So let's try and find out where it equals 0, and then those are the things we cannot allow. So this would happen if y is equal to x squared, which means, remember that has two solution sets plus or minus the square root of y equals x. So basically, our domain for this problem is going to be all ordered pairs, but x cannot equal the square root of y, or x cannot equal the negative square root of y. So if we think about that, we know maybe it's easier just to go back here, since this is a function, and basically say y cannot equal x squared. This may be easier to think about looking up here. Basically, y equals x squared is the parabola, right? So if we graph that parabola y equals x squared, we get this thing right here. So we are not allowed to be any point on that parabola, but we could be any other ordered pair in the whole plane. So basically you would shade everywhere else besides that parabola, and that would be your domain of f of x, y. So these things work pretty similarly in style to finding domain of single variable functions, but now when we look, the graphs are actually going to be two-dimensional, and our inputs that are valid are going to be ordered pairs, and our inputs that are not valid will be ordered pairs as well. So this is it. This should get you started on the 7.1 stuff. Otherwise, we will maybe talk a little bit more about some level curves and some other ideas, but then after that, we will jump right into taking partial derivatives. So this is Dr. Lennon signing off.